What if I told you we're literally on the brink of printing life itself? I mean, really think about it. What if we could just print a fully functioning human heart for someone waiting on a transplant list? Or, okay, how about printing a perfectly marbled cut of Wagyu beef without ever raising a single cow? Or, and this one is wild, a 4D shape-shifting smart bandage that actually detects an infection and automatically releases antibiotics right into a wound. It sounds completely like science fiction, right? But this is the very real, rapidly advancing frontier of bioprinting. Welcome to this explainer. Today, we're diving deep into exactly how scientists are merging technology and biology to print living, breathing tissues layer by layer. We're going to check out the machines, the materials, and the incredible innovations that are literally turning digital files into organic reality.
Here's our roadmap for today's explainer. We'll start with the basics of bioprinting, then look at how it all actually works, explore some real-world applications, dive into the mind-bending fourth dimension, and finally unpack the ethics and challenges.
All right, let's kick things off with Section 1, the basics of bioprinting, printing life. So, when most of us think about 3D printing, we probably picture a desktop machine melting hard plastic filament to make a static toy or a prototype. But bioprinting is a whole different ballgame. We aren't dealing with melted plastics here. We're dealing with fragile, living biological material called bio-ink. It's basically this liquid-like slurry made from living cells, the essential nutrients needed to keep those cells alive, and hydrogels. And those hydrogels are absolutely crucial. They essentially act as a scaffold. Often using natural polymers like collagen, gelatin, or alginate, these highly porous hydrogels mimic the body's natural extracellular matrix. They hold vast amounts of water and give the cells a safe, structurally sound environment to attach to, grow, and differentiate.
Moving right along to Section 2, How Bioprinting Works, the Blueprint.
Okay, so we have our bioink, but how do we get from a puddle of living cells to a functional piece of human tissue? Well, the journey from a digital file to living tissue happens in 3 distinct steps. Step 1 is processing. This is where we capture a patient's exact anatomy using an MRI or a CT scan. That data gets fed into CAD software to create a hyper-precise digital 3D model. Step 2 is processing. This is where the bioprinter actually deposits the bioink, layer by layer, following that digital blueprint. But step 3, post-processing, this is where the real magic happens. You don't just pull a finished organ off the printer bed, right? The newly printed structure is placed inside a bioreactor. This is a highly controlled environment that supplies nutrients, oxygen, and even mechanical stimulation, which allows the cells to multiply, reorganize, and mature into functional, vascularized tissue.
Of course, depositing these incredibly delicate cells without destroying them takes some seriously specialized hardware. Here's a quick look at the 3 main types of bioprinters. Extrusion printers are the most common. They use pneumatic or mechanical pressure to push the bioink right out of a nozzle. They're awesome for getting high cell density, but the resolution is a bit on the low side. Laser-assisted printers, on the other hand, use rapid laser pulses to vaporize a donor layer, pushing a droplet of bioink onto a surface. The resolution is insanely high, and there's zero shear stress on the cells, but they're very expensive and pretty hard to scale up. Finally, you have inkjet printers, which use thermal or acoustic waves to eject exact, tiny droplets of bioink. They're fast, great for large-scale printing, but because the bioink has to have a super low viscosity to avoid clogging the nozzle, they can be structurally limiting.
And as you can see here, the scientific community is just racing forward with these techniques. There's an absolute explosion of research in tissue engineering, with scientists constantly exploring new biomaterials. The capability to print complex internal structures, like the tiny blood vessels you absolutely need to sustain a printed organ, is accelerating at an unprecedented rate. Which brings us to Section 3, Applications and Innovations Beyond Medicine. We've talked about the nuts and bolts, but what if scientists actually achieved out in the real world? The answers are pretty amazing. One of the biggest early milestones happened at Boston Children's Hospital. Researchers took cells from patients with end-stage bladder disease, multiplied them in a lab, and manually layered them onto scaffolds to build replacement urinary bladders. 7 patients successfully received these bioengineered bladders, and years later, they remained in great health. This incredible success is what really pushed researchers to ask, okay, how do we automate this? How can we print these instead of building them by hand? But bioprinting isn't just for human medicine. Check out this number. Back in 2021, scientists successfully used 3 different types of bovine cell fibers to 3D print a steak-like cultured meat. They were actually able to replicate the complex, beautifully marbled structure of Wagyu beef. Think about the implications of that for a second.
This tech provides a totally viable alternative to natural meat harvesting, which could massively reduce the environmental impact of the livestock industry and help tackle animal welfare issues head-on.
Speaking of the environment, bioprinting is also making huge waves in bioremediation. Scientists are now 3D printing functional biofilms. Basically, by embedding specific microbes into a polysaccharide structure like alginate, they create this artificial biofilm. It protects the microbes while giving them massive surface area contact with their surroundings. These printed structures are unbelievably efficient at biochemically degrading chemical pollutants and heavy metals. It's a literal game changer for the future of wastewater treatment and environmental cleanup.
All right, prepare to have your mind blown a little bit. Section 4, the fourth dimension, adding time.
We are officially moving beyond 3D. In 4D bioprinting, objects are literally designed to change shape or function over time based on specific triggers. You might be wondering, how does a printed object know when to change shape or release a drug? Well, they engineer the hydrogels to be highly sensitive to specific environmental stimuli. We can use physical triggers, like a magnetic field, a sudden temperature change, or exposure to light irradiation. Or we can use biological triggers, like the sudden drop in pH levels that naturally happens in the body near an inflammation site or a tumor. The applications for this are completely mind-bending. Researchers have developed these things called microswimmers. They're helix-shaped nanohydrogels coated in magnetic nanoparticles. They can literally be magnetically steered through your body right to a tumor, where they release their payload of drugs, and then they're completely and safely degraded by the body's natural enzymes in just a few minutes. We're also seeing 4D printed stents that are easily inserted into a blood vessel and then triggered to expand and provide support. And remember that smart wound dressing I mentioned at the very beginning? It's a printed hydrogel that continuously monitors the pH of a wound, visibly changes color if it detects an infection, and then automatically releases antibiotics to stop it. Just incredible.
But of course, we have to talk about the flip side. Section 5, ethics and challenges, the human cost.
As we start playing architect with human biology, we are speeding towards some massive ethical dilemmas. First up is the intense debate over equal access. Side A argues that because bioprinting is the ultimate form of personalized medicine, requiring your own stem cells and highly specialized equipment, it's going to be staggeringly expensive. This could create a massive healthcare disparity where only the ultra-wealthy can afford to print replacement organs. Side B, however, points out that additive manufacturing historically drives down costs. They argue that fast mass production of standard tissues, like bone replacements or prosthetics, will ultimately lower overall healthcare costs. Plus, it could drastically reduce the agonizing wait times for the roughly 115,000 people currently sitting on transplant lists. Here's where it gets kind of philosophical. Where exactly do we draw the line between healing and upgrading? Because bioprinting could eventually be used not just to replace damaged tissue, but to enhance human performance. Imagine bioprinting bones that are way stronger and more flexible than natural human bone, or printing muscles that are incredibly resilient and completely fatigue-resistant. We could potentially print artificial lungs that process oxygen far more efficiently than ours. This introduces the dangerous yet fascinating possibility of human enhancement, potentially pushing us toward a culture that seeks to eliminate physical imperfection entirely. And, how do we even govern this? Regulators like the FDA face unprecedented hurdles here. They have to figure out how to standardize the testing of personalized, living biological structures, which are infinitely more complex than traditional medical devices. If access is overly restricted, it could totally stifle innovation. But if it's left completely open, there are severe safety risks. Selling bioprinted organs might even violate existing laws designed to prevent the black market trade of human organs, which would force a complete rewrite of global medical legislation. We started this explainer by asking if we could print life, and the answer is increasingly becoming yes. But as we transition from 3D printed bladders to 4D shape-shifting microswimmers, the technology is undeniably moving much faster than our philosophy. As we face the reality of stronger bones, fatigue-resistant muscles, and lab-grown organs, I'll leave you with this final thought to ponder. The science is almost here, for sure, but ethically, legally, and socially, are we truly ready for human enhancement?